Welcome everyone to this Inside the Industry NGA2D interview series with Dr. James Torr. Thank you for joining us today. For those of you who don't know, Dr. James Torr is a distinguished researcher of graphene and professor from Rice University and has done a lot of unique pieces of research with graphene that we're hoping to discuss today. So, Dr. Torr, I said you've done a lot of different pieces of graphene research. In your mind, what would you say is your personal favorite bit of research surrounding graphene that you've done? And what would you actually say is your most notable piece of research to date?
Okay, well, Liam, let me just mention that I think whatever your camera is, it's shaking. It keeps shaking up and down, especially as you move your hands. And yes,
Okay.
it's moving back and forth. So from my view, I think you got to move your hands away from your table or whatever's touching your camera because it keeps moving it. My favorite, it's hard to say what's the favorite part of graphene project that we've worked on. That's like asking me which one of my 4 children is my favorite. They all have a role. I think probably the one that has had the most impact so far has been laser-induced graphene. That's where we can take any surface and lase it with a laser that you just find in any machine shop, which is it's called a laser scriber. All machine shops have these, and you just do that in the open air and you form this foam of graphene on a surface. It works very nicely on a polyimide surface. Yeah. But then we found you can do it on just about any surface. And we've done it on foods, we've done it on paper, we've made pictures out of it. In fact, I'm going to try something here. That picture right there, up on the wall there, yeah. That picture is laser-induced graphene. And so we have other pictures around here made out of laser-induced graphene. So it's all conductive matrix and things like that. So but the telling thing is that there's about 2 to 3 papers per week now coming out in the literature by other groups using laser-induced graphene. So we first published on it, patented on it in 2013, first published on it 2014. And so now after 6 years, it is being used like crazy for building devices. I'd say there's more devices being built out of laser-induced graphene than any other form of graphene. It's so simple, then you can pattern it whatever pattern you want, and so you can do it whatever you like, and that has great advance. I think probably that's going to be overrun though by our new process, which is flash graphene. It's taking any carbon material and treating it with a high voltage, high current pulse at for about 100 milliseconds or less. And you get beautiful graphene. And when I say any carbon material, I mean it. Any carbon material. We can take waste bottles, waste plastic, waste food. We can take coal, petroleum coke, and convert it into graphene. And so to give you an idea, coal can be $25 a ton. But we can convert that into graphene, which right now sells for $67,000 to $200,000 per ton. So it's an enormous upcycle method. And so there's a company now that's trying to scale that and do that. We have a grant from the Department of Energy to do 1 kilogram a day in my lab from some US sourced coal. Right. And so that's what we're doing now, and we're working on it. And you know, for my lab to make a kilogram a day, now a kilogram is a lot of graphene in most people's estimation, but that's not industrial quantity, but that's just a proof of concept. Then pilots will be scaled from there, and then large manufacturing. That's what the company's out doing. But then we have other types of graphene which are already on the market and doing well. And so it's kind of exciting to see that. We have where we had made graphene quantum dots from coal. This was about, I guess about 8 years or so ago, something like that, 7 years ago. And now that's a company called DOTS, D-O-T-Z, DOTS Tech. And that company is just, just doing very well, particularly on these COVID related days, because it's being used now, and I'm not telling you anything that's not out there. It's a public
Yeah.
company now. It's being used to mark PPE, masks and things, to show that they're authentic, that they're not knockoffs, that they've been approved. And so it's for authentication, where you use little fluorescent codes.
Yeah.
So it's being used in that, and getting a lot of traction from that. And so the stock price has actually gone up in the last 6 months or 8 months. It's gone up almost 400%, which is kind of nice.
Yeah.
And so that's doing well. And then we work in other areas. But I'll let you ask a question. I've spoken a lot, Liam.
No, it's fine. I'm glad you mentioned both the flash and the laser-induced graphene, because it's a couple of areas I thought it'd be interesting to talk about. Because obviously, I'll start with the laser-induced graphene, because that, I would say, is probably not as well known to, say, the general public compared to your average graphene. I mean, some know about different types, but obviously, if you're making it with a laser on a surface, is that like a scalable technology, or is this something that we're going to see in, say, more customizable, small scale applications?
Yeah, so lasers are used enormously. Every bottle that you purchase of water has a laser scribe number on it with its information of where it came from. So lasers are used in the industry and manufacturing widely, and to a very large extent. And so things can be pushed through extremely rapidly. So remember, lasers are firing and making these patterns. And so sometimes the substrate moves, sometimes the laser moves. But these are used industrially. So for making patterns on surfaces, to use it in electronics and devices, this is very scalable. It's not to make tons of laser-induced graphene, but it's to make a lot of items can be made that way. So that's an easily manufacturable technique, and it's being used a lot. And I think those that work in the area of graphene are now well familiar with the laser-induced graphene.
Oh yeah, no, I was on about those outside of the industry, because obviously I know there's quite a few in the industry who know about it now. That was more on those who are not necessarily involved directly, but know about graphene. Well, with that then, and that's interesting to bring up about the patterning, and especially with electronics, because graphene is something that has struggled to get into electronics, like commercially, compared to other areas. Because obviously it's higher value, there's a lot more testing that needs to be done. Is by patterning with, say, like laser-induced graphene instead of other materials, is that something that could help to push graphene into more electronic devices, do you think?
Oh, absolutely. Absolutely. And that's what many people are doing. I mean, I just wrote a book on laser-induced graphene. It should be out in a few months, from World Scientific. Just so many applications, from electrocatalysis to pressure sensors, to gas sensors, triboelectric nanogenerators, supercapacitors, water splitting, oxygen evolution, oxygen reduction. I mean, so much has been done now with laser-induced graphene. I wouldn't be surprised if in the literature there were hundreds and hundreds of papers now on laser-induced graphene, and almost all of those, aside from us, our group has just done a lot of characterization. We have about 30 papers on laser-induced graphene. A lot of those on the characterization and formation properties. The vast majority of people are looking at it from an engineering standpoint. What are they able to make from it? And so it's being well recognized as a way to make devices and a way to make conductive films and conductive patterns. We've now gone down to, I think it's 12 micron lines we've published on, and we've got even finer patterns than that. So it can be done in quite fine pattern lines, where we're down to around 10 microns, maybe even single-digit microns. I know that's not the nanometer size, the 10, 20 nanometer size lines that Intel can get to. But remember, that's an industry that's been around for 60 years and has had trillions of dollars and millions of person years put into it. We're talking about something that's been developed in the last few years and has had something probably on the order of a few $1 million put into it. But you see the power of it. And for making these patterns, I think it's going to be huge, absolutely huge. And so what we did is we patented many different ways to make it and then to use it. Now other people are patenting their own special applications, but I think a lot of that is going to be beholden to the base patents.
Yeah.
And that's now in a company called LIGC. And so hopefully that will launch from there, and then there'll be a lot of joint ventures as other people want to take this and use it in their favorite application area.
Oh, it's very, very interesting. And yeah, it's great to see actually as well, because I said that's why I thought I'd ask about electronics, because it has been an area which has not been as well developed. So I look forward to seeing how this develops, because as you say, it's a new technology, like a new way of doing things. So 10-20 years down the line, who knows what we might actually see. Just for one last question before we move on to like the flash graphene side, because we put these videos out to both the graphene industry and those not in the graphene industry, could you just give us a quick summary of like what the difference actually is between the laser induced graphene, like physically or properties wise, compared to your average either like nanoplates or CVD graphene? Is there any difference?
Right. Yeah, there is a difference. So CVD will grow a single layer of graphene or a few layers of graphene. It's a slow process generally, although CVD can be made continuous. Usually it's done in an inert atmosphere, and you're making these patterns that you're growing large areas, and then from that you can pattern using some lithographic method. Laser-induced graphene is a different type of material, so we're not bringing in methane as the carbon material that's hitting a metal catalyst. It's forming on the surface. There's no metal involved here. One can just take a piece of plastic and hit it with a laser, and that laser converts it into graphene, but it's not one layer graphene or just a bilayer. It is a graphene foam that can be several microns thick, even up to, we've made several millimeters thick if you want to. So you can make it thick so you can have a larger area for sensors or arrays. And then these are conductive little lines. And then you can dope these. You can either dope them by putting dopants into the plastic upon which you're writing, or you can dope them subsequently. So you can take laser-induced graphene. You can then just dip it in a bath or spray it with a solution of a metal salt, and then laze it again. And now then you get metal particles or metal oxide particles, depending upon the conditions, forming right in the material. And you can do electrocatalysis there. So it's different. It's a foam-like material. It's not a flat material. This is a foam where you might have 2 or 3 layers, and it's going around in a foam with lots of high surface area in that way.
It sounds very versatile, and like I said, it'd be useful for other things that the other types of graphene don't have. So yeah, as I just wanted to touch on it because there will be people watching this who who don't know about it. So it's always good to cover it when you're talking about it. But we'll move on to onto the flash graphene now, and you talked about that briefly, and being able to transform all carbon materials down into graphene. I mean, that recently came out as well in your garbage conversion research. That's was published in Forbes and various other media sites around around the world. Now I'd just like to ask a few questions about that, because obviously the main one is, why did you choose any just general garbage refuse? Because obviously that's going to be a mixture of carbon materials and any other materials, and if you're flashing just like a lot of garbage, and you convert the carbon materials, what happens to the non-carbon materials in that garbage? Do they get stuck there? Are they contaminants? And how do you remove any of these if there is contaminants in there?
Right. So if you want to make bulk graphene, your purpose is to make graphene, you would generally start with a high carbon material like petroleum coke, which is very
Yeah.
cheap. That's the slag that's left off after these distillation towers, the stuff that doesn't come out, very high molecular weight. Or you'd take coal, which is very cheap,
Mm.
and you'd flash that. Now, certainly coal has other elements, but what's interesting is carbon does not sublime until about 3,800 Kelvin,
Okay.
very high. We run this, we flash it at about 3,100 Kelvin. All other elements sublime out. Silicon is gone, aluminum is gone,
Mm.
everything else is gone, and it
Right. Okay.
sublimes out. And so those can be captured, and they all come out, and you're left with very pure carbon material. So that when you're talking about waste, so say you're dealing with waste plastic. Waste plastic will, depending on the type of material, you'll have oxygen atoms in there, you'll have nitrogen atoms in there. Those are going to come out. Those oxygen atoms will come out as water or CO2. The nitrogen atoms will come out as NO2 or some other small compounds. But those are all going to sublime out, and you get to a very highly pure form of carbon. Our first paper talked about it and showed we could take all the different types of recyclable plastic, even mixed together. So there's no need to separate them. That's why you can't compete with recycling. Recycling costs more than the virgin plastic itself, certainly with the depressed oil prices today. Because what they do is they take the plastic, and when it goes in, it is separated. Human beings are separating the plastic, and it might be about 80%, 85% pure, say, high-density polyethylene. And then that goes and gets chopped up into small pieces and then washed 3 times with detergents. A lot of water is used in that process. And then that goes through an optical sorter where it goes down a tube, and at the rate in which it falls, you have these little optical sensors, and that which is not plastic will have a different density, and air blows that thing out of the stream, out of the falling stream. And that's an expensive and time-consuming process. And then that is then blended, melted down into pellets. What we do is we just take everything, and it might have paper mixed in with it, it might have detergents from detergent bottles, it doesn't matter. You heat it up, you flash it, the temperatures get so hot, everything breaks down to the individual atoms. You break every atom bond. Every bond in every molecule is broken at those temperatures. And then you get the individual atoms. That which is not carbon comes subliming out. That which is carbon will remain and form graphene. So it is an amazing process. We take all mixed forms of plastic, even PVC. PVC works great. Yeah, HCl will come out. We can trap that, but the carbon remains. And you get graphene. And you say, well, what are you going to do with all of that graphene? Well, it turns out there's a lot that you can do with it. So there's all these building materials around us. Think of having graphene in that, strengthening it, and you use less of it. So for example, we add much less than 1 weight percent of graphene. We add 0.1, 0.2 weight percent of graphene to concrete, and we increase the compressive strength by 35%, and the tensile strength goes up. And so the compression modulus goes up. So this has tremendous advantages. You can use less concrete. Concrete is responsible for about 5 to 8% of all CO2 emissions in the world come from making concrete. So if you can use 1/3 less concrete by having added some graphene to it, then you save from CO2 on the other side as well. What is the cost of converting, say, coal or petroleum coke into graphene? Well, right now our estimates are down to under $100 a ton in electricity. There's no solvents, no water, less than $100 a ton in electricity. Give you an idea, graphite right now sells between $1,000 and $3,500 per ton. And then from graphite to make graphene, you got to put in a huge amount of energy for the mechanical shearing or electrochemical opening. So $100 a ton is a very cheap material. And then you say, well, where would you put all that graphene? Well, you could put it in concrete if you wanted to. There's about, if you converted all the CO2 in the world all the CO2 emissions in the world, that's 30 billion tons of CO2 emissions made by humans every year. If you were to convert all of that carbon into graphene, you'd have 8 billion tons of graphene. Where are you going to put 8 billion tons of graphene? Well, it turns out there's almost 50 billion tons of cement and concrete produced every year. Yeah, that's a lot. So you could easily put it into cement and concrete if you wanted to. But there's other things. You put it in plastics. We've got these joint ventures now through the company Universal Matter going into plastics, going to concrete, going into asphalt, strengthening all of that material. And going into wood composites. And so there's a lot that this can be put into. The nice thing about graphene is it's generally low toxicity. Now, everything has a toxicity profile. Water is toxic. You drink enough of it, you die. So it's degree of exposure. It's how you're exposed to it. Is it injected into your veins? Is it ingested? Is it on your skin? How is it presented? But if you think about graphene in this way, graphene is already in our environment. Graphene is shearing off of graphite already in streams, and it comes off of graphite, and graphene is already in our environment. And it is not readily decomposed. If it were readily decomposed, we wouldn't have graphite in the world. Graphite is a beautiful form of graphene, just stacked up layers. And microbes don't eat it very rapidly. Again, when you talk about geodecomposition, it depends on the environment. Wow, what's the exposure to the sun? What are the oxidants that are around? But if you look at it, microbial oxidation of graphene generally is not a rapid process, hundreds of years, if that fast. And so when you can fix carbon into the form of graphene, you prevent a lot of CO2 going out. So if you can take these carbons and put them in a form, so 30 to 40% of all food in the world is disposed of. It has to be because it goes bad. That food is thrown out. When it goes into waste dumps, it forms not just CO2, it also forms methane. Methane is a far worse greenhouse gas than is CO2, can be 7 times worse. Just depends, again, on how the measurements are made and in what kind of environment. But all of this is forming graphene. It is better than taking CO2 and sticking it down whole, I think, because that CO2 that you stick down whole, you're taking 2 oxygen atoms for every carbon atom that you're sticking down whole. So when you decarbonize the atmosphere, you're also deoxygenating the atmosphere twice as much, 2 atoms for every 1 atom. And so here you form graphene for something less than $100 a ton. And it is a tremendous advance. And you're forming something that's already naturally occurring in the environment anyway. Graphene has been used in biological frameworks many times, and it shows very little degradation. Now you can expose, it depends on the sheet size. Again, it depends on how it's presented. But that's true with many things. If you present many things that we work with on a daily basis to cells in a dish, you're going to see some effect of that. But generally, you look at what is in our environment already, and graphene is already there. It's already part of our environment, and it's been with us for geological timeframes. And graphite is not a, we don't consider that a highly toxic material. So these are the things that we're talking about, and it's an attractive prospect to be able to do this, to think of treating all of this human carbon waste for less than $100 a ton. Our estimate on the plastics is that we would be able to treat 1 ton of plastic for $30 a ton and convert it to graphene. Now, it depends on how much carbon that plastic is. So high density polyethylene might be about 85% carbon. Other types of plastic might be 60% carbon. Those other non-carbon elements are going to sublime out. You capture those are going to have value. That will come out in the same process. But here again, no solvents, no washing. It could be, really tremendous for the future as we talk about being good stewards of our world and somehow dealing with this material in an environmentally friendly way. If we just throw out carbon, say as carbon black, this gets taken up by plants, becomes part of the plants, ends up in the CO2 cycle. The nice thing about graphene, because its decomposition is so slow, it is very slow to open up to re-enter the CO2 cycle. And that's exactly what you want to have. You want to have things like graphite that don't enter the CO2 cycle anymore.
Oh, very interesting and very comprehensive. And I've learned some things there myself today. No, it's a very impressive method for like a couple of reasons. Because A, just being able to get rid of any contaminants and impurities from the carbon with relative ease. And then the fact it's also eco-friendly, it's obviously more eco-friendly than recycling is. And then the fact you can put it into applications once you've made it, that then reduces the carbon footprint again. It's quite an impressive series of events that have come, that can come together with it. It's a very impressive method, I must say.
And let me just mention, so say you put it into plastic. So we have joint ventures with plastics companies. Put a little bit into a plastic composite. We have a program where we've just filed a DOE grant working with Ford Motor Company. We're going to take their end-of-life vehicles. So Ford right now is putting graphene in every one of their vehicles. If you buy a Ford that's been produced after February 2020, it's got graphene in it. So the Escalade and the F-150 has had graphene in it for a year or two, but all Ford vehicles since February of this year. So they use graphene to lighten the weight. They use it in the foams. It can be used in seat covers. And so you can use less material. There's about 180 kilograms of plastic in every vehicle, roughly, if you average it out, about 180 kilograms. At the end of the life of the vehicle, what do you do with that plastic? Right now in the US, that's just put into landfill. In Europe, there's a lot more pressure to deal with that now. And so it'll be stripped and we'll convert it into graphene. Plus, to put more graphene, as the price of graphene comes down, they'll put it more in and they'll make plastic composites that will fill the roles of what metals are doing now, which will lessen the weight of the vehicle substantially and save you on the fuel side. So again, it's a huge CO2 savings, CO2 generation reducer and fuel reduction system by lightening the weight. And so you have all this. And the nice thing about it is you can take plastic that has graphene in it, reflash it, and turn all that back into nice fresh graphene. And the graphene that was there, every bond is going to break and reform as graphene. So in that sense, you can do this over and over again.
Yeah. Yeah, it's very impressive, and yeah, the recycling aspects of it is very good. It's interesting you've brought up concrete and the automobiles and Ford, because it's not the first time I've heard them mentioned in some of my chats. It's obviously both of them are key topics at the moment, and obviously the recyclability of the flash graphene is, it's a great method, and especially with the low cost, like you said, like, is this something that could help then to bring down the cost of graphene, like across the board, and so it gets used in a lot more applications?
Enormously. So right now, again, like I said, $67,000 to $200,000 per ton.
Yeah.
There's that could, these types of processes might reduce the price by an order of magnitude. But again, what the company ultimately charges is going to depend on many factors, and that I have no idea. I'm not an officer or director in these companies, so it's not like I can reveal any secret information because I don't know any. But yeah, this is a very different ball game now. Very different than the exfoliation from graphite method.
Yeah,
no solvents, no water. Yeah.
Yeah, has the potential to bring it down if companies so wish, basically.
Mm-hmm.
Depending on, but yeah, and a lot more environmentally friendly, I said, without the solvents or the acids or anything else that's used in the process these days to create graphene. So no, yeah, that is very interesting method. I thank you for going into it in such detail. There's a lot of information there, and obviously a lot of possibilities with it, with the flash graphene, and that is another area going forward. I'm looking forward to seeing how it develops commercially and how much graphene we actually get to see, from the methods being produced at an industrial scale. I'd just like to, before I finish up, revisit one of your old bits of research from a few years ago, because you have done quite a bit of work, on the medical side as well, from like obviously antibacterial and antibiofouling services. But one of the ones that has stood out over the years is using the graphene nanoribbons to repair spinal cord in the rat. Now that came out a few years ago, and it was said when it came out, it was going to take a couple of years for the project to conclude, and then hopefully go to clinical trials. I just thought, because I've not heard anything since that initial reporting. You know, what has been the like status and results of that, and is that something that could be taken forward?
Well, that's been transitioned to a company called Neurochords, and they're working on peripheral nerve and spinal cord, and they have a number of internal studies that they've done. And then we have done more with a group in Colorado on optic nerve repair. So there's not a whole lot that I can tell you from what's going on in the company.
Yeah.
Medical things are always hard to do. So I don't have an update on the details of what's happened in the company. But from the optic nerve repair, we have seen some promising results for optic nerve repair from this sort of work. We've not yet published on it. So that's on the graphene nanoribbon side. And we have other things that we've done with graphene and in the medical area.
Good. Yeah, I appreciate you can't say it. The fact that it's gotten the research has gone then to the company stage is testament in itself that that there's a lot of potential there. So that that is a development in itself and progress on one scale. Obviously, you can't say anything about it, but that's what it is. What it is, and good to hear about the other areas being promising as well. So that's something that we can all look forward to seeing in the near future as well. So yeah, that was just basically. I just wanted to see if there's any updates on that. So we'll we'll move on to like the final side, and I want to find out what your vision is for graphene in the future, like both short term in the next few years, and then in the long term over, say the next decade or so and beyond.
So generally, when you come up with a new material, it takes a long time to get it into the marketplace. So we have a 2004 discovery, and so we're 15 years into it. Graphene is now 15 years old. Even though it was discovered first in the early 60s, the real launching point, we'll say, was around 2004 with Gaiam Novoselov in Manchester. And so I think that certainly within the next 5 years, we're going to continue to see small insertions into small places, and we're going to see this. But within the next decade, because the price of graphene is going to be coming down substantially, I think it's going to be in the most materials that we see. It's going to be in most materials. Just like it's in every Ford motor vehicle, in 10 years, it's going to be in every motor vehicle that you see. It's going to be in every plastic composite. Just like there's plasticizers in plastics right now, every plastic you look around, you see it's generally got a plasticizer in it, doing some function. Generally, that's a mechanical function, and there's other materials that are added to plastic. Let's just say the mechanical function, and I think that you'll see it in all sorts of plastics. You'll see it in other devices, and it will also be quite abundant in the area of medicine, because what Universal Matter plans to do is to also start a GMP, a good manufacturing practice line, that will make something on the orders of kilos rather than tons, that will be for medical devices, bone composites, composite limbs, that you'd have this. And so then you're going to start seeing it certainly in the medical device area. And then also in the drug area. So we're looking at small particles of graphene. We just published on this recently, made from activated charcoal, which is already an approved GMP source of carbon. We take that activated charcoal and we make graphene quantum dots out of it, and oxidize them, and using those medicinally. So I think it's going to be in everything from medications to makeups to bone composites and medical applications. And then in the materials that we see around us, it's going to be in seat cushions and in seat foams, And I think all plywood will have graphene as part of the adhesive layer. They're going to put graphene in that to give not just an adhesive, but to really increase the mechanical strength so that you can use less wood and have the same mechanical strength. So you're going to see that in a decade. You're going to see it hugely in 2 to 2.5 decades, because again, it takes time to broadly incorporate things. So I think that that's a realistic time frame. And this thing that the press always wants to see things overnight put in, that's never been the case. Never been the case with normal plastics, never been the case with devices. Things take time to become ubiquitous. But this is growing rapidly, and especially as the access to it grows rapidly. And you can take these graphene powders and just disperse them in things using water and a little bit of a surfactant. They'll suspend, and you can get very nice insertions. So I think that that's what you begin to see.
Yeah, it's interesting because I heard it before about it's going to be everywhere, but we might not necessarily know. It's kind of like in stealth. It's going to be in like stealth mode. It's going to be there, but we might not necessarily know it's there. But it'll be in everything. And you make a good comparison with, say, like the plasticizers and other additives that we have in our everyday materials. It's likely to become a similar type of material. And I also agree about the hype train of the media. I know it's very counterproductive, but we have to live with that. It's but and yeah, so that is going to lead me on to my final question. And it's kind of a follow on from the vision. It's like what areas? Obviously, you've said it's going to be in a lot. You think it's going to be a lot of areas, but which areas do you see graphene having like the greatest impact on society over the coming years? And why do you think these areas are going to, be impacted the most?
Well, I think that what we're going to see, if you want to talk about impact upon humankind,
yeah,
I think that the impact upon humankind is going to be most felt in the reduction of CO2 entering the atmosphere because of the use of graphene in materials, which is going to make the materials, you're going to need less of the materials themselves. And that's going to spare our atmosphere of a lot of CO2 impact. And so you'll find lighter materials that are stronger, that don't take nearly as much energy to make. And that's where we'll see the impact. The other thing that I think is underappreciated, I've spoken about it a little bit, but I'll say it again. So if you look at combustion, you take, for example, natural gas, say methane, and you combust it to CO2 and water. That will put out about 800 kilojoules per mole. If you take methane and you strip off the hydrogen atoms from it to make carbon plus 2 moles of H2, and then you use that hydrogen, those 2 moles of H2 in a fuel cell, then you generate electricity. There's been no CO2 emission. Those processes are well known. Those two combined thermodynamically are 400 kilojoules per mole of energy emission. So you only get half the energy out of combustion, but you have no CO2 emission, and you get much of that energy back because combustion, say in a car, is only 25 to 35 or 40% efficient, depending on whether you're in town or on the highway, whereas a fuel cell is 80% efficiency. So you have twice the efficiency from a fuel cell. So you get part of that thermodynamic loss back just because of the efficiency of it. Plus the process for stripping the hydrogens off from carbon has been around a long time. For example, it was called furnace black. That was developed in the 1950s, 90% efficiency. They just didn't know what to do with all that carbon. Well, if you take that carbon and turn it into graphene, now you have a good use. If you just take that carbon and throw it out as a fertilizer, it's going to enter the CO2 environment again. It's going to go into plants and go into matter, go into the environment and turn into CO2. If you turn it into graphene, it's going to be very slow to enter the CO2 environment. And if you just slow these things down by 100 years, you win.
Yeah.
Because if it's at 100 years, in 100 years, we'll have different energy sources, which are not going to be carbon-based. In the short term, you may say, well, we can make batteries. Well, you got to charge the batteries somehow. You don't have enough sunlight extraction ability or wind extraction ability yet to really exploit that. So if you need carbon, this is a great way to deal with it. And so again, I think that the impact here of graphene fundamentally is to reduce CO2 emissions by having a huge impact on materials.
Excellent. That was a nice summary of everything. And yeah, so yeah, it should be a really exciting prospect to actually bring down the CO2 emissions. And I like the way about bringing some of the old techniques back, you know, and everything being made again and that. And yeah, fuel cells are another developing area, which hopefully we'll see more of. Yeah, no, I do like the environmental aspect that you've brought today and reducing the carbon footprint, because it is one of our world's key issues. So it's great that you know, are mixing graphene with this, let's say, you know. That's been really, really good to see, thinking about the bigger picture. Right, so that concludes all the questions I have for you today, Dr. Tor. I would like to thank you for joining me on the NGA interview. I hope everyone's found it interesting, and until the next video, goodbye. Thank you.